Greetings. Today I want to teach you how to do all sorts of calculations on compressors. The compressor that we want to talk about today is a compressor that is drawn in this way. We usually draw a shaft, a rotating shaft, where we put work to it. There is an incoming air in this problem where the pressure P equals 120 kilopascals and T equals 20 degrees C. These are this is the incoming air, and its volumetric flow rate V dot equals 10 liters per second. The outgoing air has a pressure P equals 1 megapascals, 1000 kilopascals, and its temperature T equals 300 degrees centigrade. Now, that is all we know about this compressor, and what we want to use is that we should calculate its work. How do we do that? We simplify the governing equations for it. And how we simplify the governing equations? We decide on a control volume. So the initial step for doing any calculations on it is to decide on a control volume, which would look like this. And this control volume has an inlet, an exit, and also there is work that is done to it. So work should be negative. Now, the first step for calculation is this one, and the second step is to write down the governing equations. The governing equations that we have are four equations. As you see, this is the mass conservation equation. This is the energy equation, first law of thermodynamics, second law of thermodynamics, and also the availability equation. And we will have a look at all of them for different processes that could happen. We would first start with this process, which the initial and final conditions are known. Then we would calculate the isentropic process and sort of ideal process. Then you would calculate an isothermal process, and you would compare whatever that you could get from them all. So now let's start with the mass conservation equation, and the simplification of it would be zero, which is dmscv by dt, which is the change of mass inside this control volume, which, as we assume the problem to be steady, then the change of mass in it is zero, equals m dot I minus m dot E. This is the mass conservation equation, and so it really is concerned with mass. What we are given is volume flow rate, and the volume flow rate is quite often used in industry, true, but at the same time in thermodynamic calculations we need to do mass, and volume really does not come into laws unless we use we change this mass as volume and specific volume and then do the calculations that we have already done quite often. So, as for the volumetric flow rate, it is perfect gas. So, P, we could write for perfect gas, P V dot equals M dot R T. And for the initial case, we know all properties, and so we could relate V dot to M dot. And M dot would equal P, which is 120 kilopascals, times V dot, which is 10 liters per second, which is also 0.01 cubic meters per second, and divided by 0.287 kilojoules per kilograms Kelvin, and this is kilojoules per kilograms, this is kilopascals, so they match. All the SI units is pascals and joules, so they all are multiplied by 1,000. We could do that, or divide, they are now divided by 1,000. That is okay. Times 293, which is the temperature, 20 degrees centigrade plus 273, and that would equal 0.01427 kilograms per second. And that's the value for M dot that we shall use from now on. Okay, this is the mass conservation. Now we go for the first law of thermodynamics. Have a look at the first law of thermodynamics, and the first law tells us the change of energy inside the control volume, which is zero in this case because it's a steady flow and there is no change for whatever that is inside our control volume, is the energy that enters with the mass that enters. We ignore all changes of velocity and all changes of elevation, and the inlet and the outgoing mass are equal. There is no heat transfer. The problem tells us that for the time being, the compressor is adiabatic and there is work. So to simplify this equation, it would look like this, which is 0 equals m dot times hi minus he and minus w dot. For the time being, it is said that q dot equals 0 and the compressor is adiabatic. Of course, this is a good idea since we really want all the work to increase pressure. We want all the work to be used to increase pressure. We don't want the energy given to be wasted as heat transfer unless there is a purpose for it. If there is a purpose for it, fair enough. But if there is no purpose in heat transfer, then it pays that all the work should be there to increase pressure. So this is an idea for the compressor. There are some compressors which are isothermal, which have constant temperature, and therefore they have some heat transfer. It depends on different compressors have different ideas and work differently. And we shall also study this compressor for an isothermal process. Okay, now Um, what we have here is that W dot would equal 0.01427 times CP0 delta T. CP0 is 1.0045 and times the temperature difference, which is 293 minus 573. This is 20 degrees centigrade and this is 300 degrees centigrade. And the final outcome for work is minus 4.014 kilowatts. This is the work that is required in this compressor to increase pressure from 120 kilopascals to 1 megapascals and with this exit temperature. This is the process that we are talking about. Okay, now, could we draw this process on different diagrams? This is a practice that we usually do. And one diagram that we could do, and is very useful, is a TV diagram. This is the TV diagram. And we should first draw constant pressure lines on this diagram, which they look like this. These are the constant pressure lines. This is P equals 120 kilopascals, and this is P equals 1000 kilopascals. You see, it's always a problem, always a confusing problem, whether these lines on this diagram should look like this or should be in this way. Okay, which one is correct? And the answer you would simply find if you look at this equation. You see, P is constant, so V increases with T. V and T increase together. So this is the way these lines are. Another diagram which we could draw for this problem is the PV diagram. This is P and this is V. And now we have to draw constant temperature lines on this diagram. Look, if temperature is constant, R is constant, therefore P and V change in different directions. So if P drops, V increases. So this would be the constant temperature lines on this diagram. So this would be the 293 kelvins, and this would be 573 kelvins. These are the two constant temperature lines on the PV diagrams. And what we have to do now, these are properties of air. It has nothing to do with our problem. Now we have to install our problem over this diagram and show where our problem is. Well, to draw our problem on this diagram, we have pressure and temperature for inlet and exit air. But to draw a diagram up to scale or somehow realistically, we need to know specific volumes as well. And that's very simple to calculate. Just from the same equation, we could write VI equals RTI divided by PI, which is for the inlet condition, and that equals 0.287 times 293 and divided by 120, and that equals 0.7 cubic meters per kilograms. Also for VE, the same equation shows that RTE divided by PE, and that equals 0.287 times TE, which is 573, and divided by 1000. And the outcome is 0.1645 cubic meters per kilograms. Now you see the inlet condition is a 293 is on 120 kilopascals and has higher specific volume than the exit condition. So if we want to show it on this diagram, show our process on this diagram, look, this could be the I, where this could be I, where a specific volume is 0.7, and as for E, a specific volume is smaller, pressure is higher, and also temperature is higher. So E could be somewhere like this, where specific volume is 0.1645 cubic meters per kilograms. That's the two values. And for temperature, this temperature is the inlet temperature 293. Its units is in kelvins, and the exit temperature is 573 kelvins. And that's our problem on TV diagram, and the process, if we draw it, would be this one. The process is this. This is the process. Okay, this is the process that happens inside our compressor in a TV diagram. What happens in the PV diagram? You see, the initial point is somewhere here, and the final point is on this line at a lower specific volume. Call it this one, and the higher pressure. So this would be point I, this would be point E, this is 0.7, and once again, cubic meters per kilograms. Pressure is kilopascals, and this is the exit pressure. This is the inlet pressure, which is 120, and this is the exit pressure, which is 1000. And our process is this one. So it's a fairly good drawing of this problem, since the inlet and exit are correct, specific volume drops, but temperature and pressure both increase. And this is a TV diagram and a PV diagram for a compressor. Later on, when we come to the second law of thermodynamics, then we would draw the problem on a TS diagram and complete our work for different diagrams. Now, the other question that the problem asks us is that what happened if the problem was isothermal, if the temperature remained constant? So the other process that the problem asks us for is that what happened if the process was isothermal, isothermal process. That means that there was so much heat transfer that the temperature remained constant. Now, our first step is to show you how an isothermal process would look like on these diagrams. Now, on this diagram, the initial point would be this one, and the final point would be this one. The green line is for an isothermal process. So the green E is an isothermal process. What from this drawing we expect, and if we have drawn it correctly, is that the specific volume for an isothermal process would be less than for an adiabatic process. What happens here? Here, for the same temperature and the pressure is 1000, so E would be here, and the process would in fact be along the constant temperature line, like this one. So our green drawings is for the isothermal process. The first thing that we do, as always, is to simplify the conservation equations for the isothermal process. And that looks like this. 0 equals m dot I minus m dot E. And it is the same for this one. The mass remains constant and it's exactly the same as before. So we just write it m dot I equals m dot E, and that equals 0.01427 kilograms per second. No change is done for the mass. This is 14 to 7. Now, as for the first law of thermodynamics, the change is this, that 0 equals, because even when it's isothermal, there will be no change in whatever is inside this controlled volume. It's a steady state, steady flow process, and therefore it is m dot times hi minus he plus q dot and minus w dot. And the point is that since the temperature is constant, you see, for constant temperature, hi minus he is Cp0 Ti minus Te, and since the temperature is constant, this term cancels out. The outcome is Q dot equals W dot. We have no equation for the time being to calculate either of them. For Q dot, we have no equation, and for W dot, we need an equation to calculate it. The equation integral P dV was valid for a system. It was valid for a system with moving boundary. It had to be very slow. Now, what is our equation for a control volume? And the only equation that we have for an isothermal flow, I mean, if it is if it is reversible, plus isothermal. And for such a case, we could write that W equals minus integral V dP. Quite opposite to that P dP. This is minus integral V dP. So this is an equation for a control volume, and it is valid for a reversible isothermal process. You see, this process didn't need to be reversible. We had no idea about this being reversible. But this equation should be reversible. Otherwise, we have no way to calculate it. So this is what we learn in the second law. Second law teaches us that for a reversible process, this equation is valid for an isothermal process. So now we are in a position to calculate work for an isothermal process, this process, or this process, which is the same. Well, the classic method for calculating this integral for isothermal process is to write, since it's perfect gas, we know that it is PV equals RT, and since the process is isothermal, it means that temperature is constant, and therefore at any point over the process, PV equals some constant value, which could well be the initial value, which is PI VI. And therefore, V would equal PI VI, which are known values, divided by P, and replace it in this equation. It gives us W equals minus PI VI integral dP over P, and integrated between initial and final conditions would equal minus P V ln P over PI. Inserting values for it, W dot would equal mass flow rate, which is 0.01427 times minus 120, which is the PI, times this minus is this one, which is for W, times VI, which is 0.7, and ln 1000 divided by 120. And W dot would be 2.5415 kilowatts. This is the work for the isothermal process. Is it positive or negative? There is a negative beside it, and that is now correct. You see, the isothermal process requires less work. For the adiabatic process, we needed 4 kilowatts. And for isothermal process, we need 2.5 kilowatts of work. That is a point to remember. We shall talk about it later on. It's a very important point. You see, if we do not want to heat the compressed air after that, in gas turbines, we heat the compressed air, and therefore it's best to lose heat. But in many other uh, applications, the compressed air cools down anyway after being compressed. You see, where they inflate automobile tires, the compressor compresses air but doesn't keep it warm. The compressed air goes into a tank and cools down. So if the uh, application is for cold air, and the air would be cooler later on. If the air would lose its temperature later on. So it could as well go through a constant temperature process. The compressors for such processes have fins where they keep the temperature of air constant. That would require less work. And this is what we see here for the two processes. This process would require 4 kilowatts, and this process would require 2.5 kilowatts. In the same way, this process would require 4 kilowatts, and this process would require 2.5 kilowatts of work. It depends what we would need after we have compressed the air. Okay, up until now, I have concluded whatever we could gain from the mass conservation equation and also the first law of thermodynamics. In the next video, we shall move to learn from the second law of thermodynamics and also the availability equation. Cheers!